What's up everyone, welcome back to my channel. Today we're going to look at a calculus problem that is actually not quite common to be seen in calculus course, which is to evaluate the derivative of absolute value of f of x, where of course f of x is just any function that we can think of. And certainly we'll assume that f of x is continuous and differentiable at some point, otherwise there is no meaning of taking the derivative of it. So we'll just talk about what the result is first, then we're going to see why it's going to be true. So let's get into a conclusion first. The derivative of the modulus function, or the absolute value of any function that we have inside, is actually equal to the absolute value of the function divided by the function itself times the derivative of the function. Maybe you wonder how we can actually get that. Here is actually what we can do. First, let's consider that we have the function f of x is just x. Then we actually get the function which is absolute value of x here, and then we're going to take the derivative. Now, if we try to consider the graph of the function, we actually have the piecewise function such that before x equals 0, or when x is less than 0, we have y equals negative x, where when x is greater than or equal to 0, we have y is equal to positive x. And of course, in this case, we will say that when x is equal to 0, y is equal to 0, but we can clearly see that there is no derivative when x is equal to 0, because we actually have a sharp point. Now, since we want to have a general situation, we can just somehow ignore it, because only a certain points, or finitely many points, that are not differentiable will not affect how the general expression of the derivative of a function will look like. We just need to remove those points as we try to evaluate at those values. So since we have the absolute value function here, we can now break it into two parts as the derivative of just positive x when x is greater than 0, and the derivative of negative x when x is less than 0. Then of course, as we divide both of them, we actually get that the first part is going to turn out to be positive 1, and the bottom part will turn out to be negative 1. But what do those actually help us? Well, if we think about it, positive 1 when x is greater than 0 is actually the same as absolute value of x over x itself. As x is greater than 0, we don't have to worry about divide by 0 in this case. Where where the derivative equals negative 1 will actually be equal to absolute value of x over x as well. And because now we have x is less than 0, we have a positive over negative x value, and then the x value will get cancelled out. And again, because x is not equal to 0, we do not have to worry about divide by 0. So now we can actually combine these two results together and claim that the derivative of absolute value of x is just equal to the function itself, absolute value of x over x. Then we can now use the u-sub to take the derivative of any function. So here is what we can do. We can now move on and say that let u be equal to f of x. Then we get the derivative of the absolute value of f of x is of course equal to d over dx of f of u, of is equal to d over d dx of absolute value of u. But what is d dx here? Well, if we look at this function here, this is the same as du over dx is equal to f prime of x. Again, that is same as taking the derivative on both sides with respect to dx here. So we can also say it as du is equal to f prime of x dx. So as we try to do that, what we get is we have this is d over dx. We can kind of rearrange it as we can get 1 over d du over dx times 1 over u, and then times absolute value of u, which actually gives us that we have here is what we have, the f prime of x times absolute value of u over u here, which again is just f of x with absolute value over f of x without the absolute value. And this is how we actually get the results up here. Of course, there are some tricks that generally speaking will not be allowed, such as we can just put a u here and divide by 1 over u. But in results, this is what we are going to get. So how can it help us? Well, if we try to do the absolute value of some trig functions, for example, such as absolute value of sine of x, then if we try to find out the first derivative of such function, we can actually use this to generate what we really want, and also see that whenever we have sharp points, when x is equal to the value of pi, some integer times pi, we will be able to show that it will, this derivative do not exist at those points. So pretty cool, huh? I'm pretty sure that most teachers will not even talk about what happens if we have absolute value here, and even if they talk about it, they will just suggest you to try to break it into piecewise function and take the derivative of it. But again, if we actually have functions such as absolute value of sine of x, we will have infinitely many sharp points, such that when we try to take the derivative, we need to break it into infinitely many. Of course, it's still countable, but it won't be finitely many piecewise function. In that case, what would be the best way to do it? We need to use some tricks in order to make it work. And here is a trick that we can actually make a lot of functions being differentiable into something that we are actually looking for, without trying to break the function itself into several pieces and try to figure out each piece. I hope you all enjoyed this video. I will see you guys next time.